Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is Peter Braam. He is long known in the HPC industry for a number of inventions, including helping develop Lustre in the first place. But Peter, welcome to the show today.
Nice to be here.
Well, Peter, it's great to talk to you. I saw your talk in South Africa about TensorFlow, and I was just captivated. This is very exciting stuff, and I wonder if you could just catch us up. What is Peter Braam working on these days?
So Peter Braam is just doing research, you could say.
Yeah.
I remain very interested in lots of solutions related to HPC and machine learning, and I try to bridge a little bit the areas that I've worked in to listen what are other people doing, what's happening with chips, what is happening a bit more on the mathematics side, and so I'm not terribly focused, but TensorFlow is something that I accidentally fell into after being offered a wonderful tour at CERN. They said, you have to do something for us now. And I said, maybe I could tell you how TensorFlow hangs together. These were people at CERN doing machine learning. And so I spent a few months really understanding what TensorFlow is. And I did that from my angle, not really a machine learning angle. And so here's this talk, TensorFlow for HPC, that came out of it. I have a few other activities going on that we'll talk about at another time, I think, related to memory technologies and related to machine learning algorithms replacing simulations. And so these are, I think, exciting things that people are looking at and worth discussing.
Yeah. And of course, I read your name connected with the SKA telescope as well. So there's a...
Yes. The SKA telescope is still very central. And actually, we will perhaps touch on it in this talk. I don't know if I included those slides, but this talk today is definitely something that the SKA community should keep an eye on as a possible compute platform.
Okay.
So shall we go?
Yeah. I brought your slides up, Peter. Why don't you go ahead? I'm on slide one.
Okay, so slide one asks the question, namely, is Google's TensorFlow platform something that can be used or explored for HPC? And so before we jump into that, you probably know who I am, but it's perhaps good to take a quick look at my career, then you understand a little bit how I ended up here. So I worked on pure mathematics and physics for really as an academic until roughly 1997. And then I transitioned into the computing industry, and I did a few startups, all related really to what is now called research computing. And as Rich just mentioned, Lustre came out of that. It was actually, Lustre is 20 years old this year. So I started that in 1999, very, very early in the year at Carnegie Mellon. From 2013, I've paid less attention to companies, and I started to work with the SKA, the Square Kilometre Array Telescope community at Cambridge, helping them to design their computers and algorithms. And so since these days in industry, I've had the privilege really of working with a lot of large compute centers and with many of the vendors who make chips or systems and storage devices. And so I think in this world, like, what will be built next, what is missing, and that's I think what we are going to see today. As I said before we started, really, I decided to offer the high energy physics machine learning community a systems perspective of TensorFlow. So not really looking at TensorFlow as a toolbox for machine learning, which is what it was built for, but really, what is it in terms of compilers, platforms, operating systems, and so on, and chip design. And I came away just very impressed and very excited about how this platform had been put together by Google and what the promise is. So let's take a look at that. So TensorFlow is now very widely used and has really gained a lot of ground on other packages. It was only openly released, I think, maybe 3 years ago or so by Google. It had been worked on before, and it has really a lot of flexibility for deployment. The deployment really can vary from a cell phone to some ultra new supercomputer depending on where you need to run your algorithms that you've developed with TensorFlow. The development tools are excellent, and the performance that is achieved is really very high. It's a masterpiece of engineering. I think there are very few projects that have impressed me as much as TensorFlow in terms of all the people that contributed to it and the awesome speed with which it's come together. For example, Google released 3 versions of a chip in 3 years' time. You know, that's almost unmatched in the industry to be able to do the updates so quickly. They pulled a lot of specialists together, both software people, hardware people, machine learning people. And I think from the HPC perspective, this is really a door opener for new accelerated processing unit design. So I called it an XPU on the slide. And here what we're seeing is that when you do domain-specific computations, in this case, you know, matrix stuff for machine learning, there is actually really a lot that you can do that wasn't done yet in processor development until now. So why did Google do this? If they realized something like 10 years ago already that their AI efforts could easily mean doubling their data centers, and this would have to be done if people only did a few voice searches per day. The amount of computing that requires is massive across the world. And so they started to realize, boy, we need to be very careful because doubling the data center is very, very expensive. Secondly, they realized machine learning and AI will be in many of our products. So we will have so many projects that pursue machine learning solutions. The development productivity is really key. So Google released TensorFlow in 2015. It's a second design following another system called Disbelief, I think. And TensorFlow scope is really profound. It offers a language, a domain-specific language for machine learning computations. It has a compiler, it has chips, and then it has lots of tools and DevOps. And really in 30, 45 minutes, we can't look at all of this, but we can look at a few of these aspects and see what they are worth. So this is really a mega project. Google hasn't really released the numbers that they've spent on it, but it's easy to see that this is something that runs into the hundreds of millions to billions of dollars. So much was created for it. So for Google, for TensorFlow, the challenge was high productivity software development, portability from phones to massive clusters, and the lowest cost performance ratio. A similar project in terms of money numbers is perhaps the telescope, the SKA telescope. That's a project on the order of $500 million, and it has its own challenges. But again, here it must meet budgets. It has also very, very high performance computing in it. And just like in TensorFlow, the productivity of the software development is very, very important. So that's a central element. So when you look at these mega projects, which, there are always a few going on, they are typically handled with co-design. And so you can see a little bit about co-design on slide 7. So co-design means that different groups of people from different angles contribute to an architecture for the solution. And so there are executives who lead the effort, there are experts. We already mentioned that for TensorFlow, there were, language experts, chip experts, compiler experts, deployment experts. Then there are users who usually have an enormous amount of input to tell people what they need and tell people, the developers and experts, when it's not good enough yet and so on. IT is a big part to get it deployed. And there are relations with vendors always, people that build the chips or sell other things. And this management of co-design is actually a very difficult thing to do. Yeah, it's very easy for small numbers of people to get ahead or to get out of touch, and managing a co-design effort is not at all so easy. But they are taking place all the time, and I think many are successful. So let's begin to look at the technical part of the story. So TensorFlow is a layered system for machine learning. And so the picture on this slide 8 shows you some of the layers. So at the top, there is really a machine learning focus. And this is what is frequently discussed in courses and so on. And Google has made it very easy to have all kinds of canned solutions for many models that can be connected to data sets fairly easily. Layers can be built and experiments can be done with that. And that is probably the part of TensorFlow that machine learning people use every day to develop their algorithms and eventually deploy them and use them. Below that, there's a Python front end, and Python really interprets the TensorFlow commands, as we will see, and compiles them into something that a runtime engine can handle. Yeah, and so there's a special TensorFlow execution engine that takes these codes that are generated by the Python front end or by some of the other front ends, although I think the front ends all ultimately feed back into Python maybe. The runtime itself is written in C++. The runtime runs on CPUs, GPUs, on Android phones, on iOS, and it can be further compiled with a lot of optimization for some of the same platforms, like the phones are typically running compiled TensorFlow, and Google developed a special chip called the Tensor Processing Unit that you can run TensorFlow commands on. So let's look at that core. On the left side, you see a very simple data flow diagram where the inputs are at the bottom and the output is at the top, and this is simply a matrix multiplication. And so the operation is in this case a basic TensorFlow operation that can take a matrix and a vector. So tensors are generalized matrices and vectors, and these TensorFlow packages is really a data flow environment for tensors to put usually relatively simple linear algebra expressions together, but doing that in a clever and efficient way. So there are different names now for everything. So a feed is used for this input data that we have at the bottom, and a fetch is used for the output data, but that's just a word. Yeah, there's not much no special meaning for these words beyond what you already think they are. So what you do in the TensorFlow core is you express these kind of graphs. And so you mention what operations and what data dependencies exist. And TensorFlow treats that graph declaratively. That means it isn't really executed right away. It is first defined. And that means that the TensorFlow engine can do lots of optimization on this graph. So for example, it can split it into two graphs to run it on two computers. And it can do that in multiple ways. It can say some of the data goes to this computer, some of the data goes to that computer, but it can also split the computation, saying some of the computation happens on this computer and the other computation happens on another computer. So this is a good approach for TensorFlow to use. These declared graphs are good to manipulate. Yeah, they're things you can compile and things you can do things with. You can eliminate a lot of things from it that you don't need, and the declarative approach is now is quite popular for complex computing. So if we look on the next slide, 10, the execution of the graph is in principle quite simple. Yeah, the TensorFlow engine will look at one of the outputs, one of the fetches that the user won, and it will find the dependencies. And so it is going to check what other numbers do I need, what other tensors do I need to get the output. And based on that, it goes backwards through the graph and evaluates what is needed to get to the output. So this is called lazy evaluation, because the only things that are computed are the things that are actually needed. Yeah, that's what the dependency checking ensures. So this is different from eager evaluation, where everything is evaluated as soon as it's encountered. This makes it much easier also to embed parallelism, because while you're checking the dependencies, you can see blobs of computing that don't depend on each other, and so they can be executed in parallel. Yeah, so again here, the declarative and lazy evaluation are a good way to get some parallelism. So the challenges that Google faced for this execution framework were quite a few. So it needs to run on distributed systems. Yeah, many of the data sets are petabytes in size, and so they have to be run on very large clusters. So graphs have to be split, data has to be fed to multiple architectures, and there's a control architecture to coordinate all the jobs that you get in this way. There are also a lot of optimizations you can do. So in particularly machine learning computations, there are often very, very many inactive nodes in these data flow graphs. So these are computations that don't do anything because perhaps there is zero inputs, or they were an expression that is otherwise not used, because some computations are sometimes deactivated in machine learning. There are also operations that do nothing. And on top of that, there are lots of constants floating around that you could perhaps not read all the time, but you could simply embed them in the code. So this is the sort of thing that the optimizer can do in the runtime, is remove what you're not executing, put the constants right in there before you start computing. A compiler was developed, and the compiler is called XLA, for Accelerated Linear Algebra. It has two modes of operation. So one is just-in-time compilation, and this means that while the algorithm is running, suddenly some fast code is generated. And because it is done just in time, TensorFlow will know what is the size of the matrices I'm working with, how shall I chop them up with tiles and that sort of thing, and it can do that for different architectures and memory layouts and so on in different ways. Another mode is ahead of time compilation, to simply create a standalone binary, say for a cell phone. So lots of optimizations can be done here. And many of these optimizations would be very, very difficult for programmers to do one by one. So for example, the queue lengths to shuttle data through these graphs is actually quite difficult to adjust, and TensorFlow takes care of that. An example is on slide 12. There you see graph modifications for distributed execution. Yeah, and we already said sometimes some data is sent to different nodes and different computations take place. And yeah, you see how the graph on node 0 is split into two graphs with special message channels. And so again, here, coding messaging into your program is a difficult task, but the TensorFlow compiler takes care of that. Good, so let's begin to look at the hardware platform. So there are many execution platforms, as I said, for TensorFlow, and typically it's used by developers in Docker machines, and all you need is a Docker machine with Python, and you can run TensorFlow with lots of debugging tools, and you can even invoke a GPU connected to a Docker image. But if you're doing training and inference for production and you're a company like Google, you will encounter huge scale. And so in this case, acceleration is possible by using GPUs. They are very popular in machine learning, as you've probably heard, and FPGA acceleration. And the compiler, the XLA compiler, simply will create the code for it. There is very little a programmer needs to know to use these platforms. There are also custom TPU processors, which were developed by Google over the last probably, I think maybe 6-7 years or something like that. So on slide 14, we have a few pictures of these. They are accelerator cards, and they sit on a PCI bus in a commodity server. And the newest one is the blue one. What you see is that it's liquid cooled. That's these gray pipes on top. And you see that there are 4 chips sitting on that accelerator board. And these are called the tensor processing chips. I think that there are then subsequently 4 of these cards in a server. So you get 16 chips. And then inside each chip, there are, I think, 2 or 4, depending on the version, matrix multiplication units. So there is just through the numbers, a lot of processing added on these PCI slots. So Google deploys these in something that they call pods, PODS, where they're really clusters. And what you see here is a rack, and it looks a little different than an HPC rack, but it's essentially very similar, with communication cables for I/O and other data, power, cooling, and so on. Yeah, and the pods are quite large, and in a minute we will look at some numbers. But the TPU v3 at the bottom has ultimately 1,000 of the accelerator cards in them, or 256 nodes. Yeah, and so that is that's not a small cluster, not a very big cluster, but when we'll see the compute power that comes out of it, it's really a lot. So the special thing about the TPU chips is a special matrix multiplication unit, the MXU. And the way that this roughly works is that an MXU has tens of thousands of little compute units, and it has connections between them. And so what you see on the left side is a lot of queues with data. So these could be elements, for example, in a vector, and there will be hundreds of elements fed into the chip, into the MXU chip, and then they will be processed on. They will not be written back to memory. They will be moved to another cell where the next multiplication takes place. So this is very suited for things like matrix multiplication, where one element in a matrix is seen by many other elements in a vector that you might be multiplying with this matrix. And this is called a systolic architecture. I think it just relates to a lot of data movement without writing data back into memory. And it was quite popular in the 1980s, 1970s, but it's only now, I think, that it is really being productized. So there are in total hundreds of thousands of these arithmetic and logic units, or on the order of 100,000 of these units in one of these chips. And what results is an enormous processing power, namely on the order of 100 teraops per cycle. Yeah, and that just comes by multiplying the number of units we have with the number of operations. Without much data movement, the data movement is just into the systolic chip and then out of the systolic chip. So the system organization is shown on the next slide. And what you basically see is that there is a TPU server that creates the code. And the code is quite interesting. It is sent to the chip over the Google remote procedure calls, gRPC. And so Google uses that both over PCI and over TCP/IP. And in this case, the instructions of these chips are actually calls. They are remote procedure calls. So it's very different. There's no instruction register. There are no fetches of instructions. You tell this accelerator card, this is what you're going to do next. And this works really well when you have big chunks of data that you need to operate on. Yeah, so it's quite different from a CPU. And again, the XLA compiler will create this code just in time, adjust the data sizes of blobs of data and so on that they send to the accelerator cards. But the latency here at the moment is still quite high. So you really want to use this when you have a lot of data and you can keep using the same algorithm that has been compiled. So the next slide shows you perhaps why we should be pretty excited about this. So the TPU v3 specs, they've been partly released by Google in an announcement, and I made some conservative guesses based on the v2 chip. And so let's look here. So the TPU 3.0 has one card, 4 chips per card and 16 of these matrix multiply units. The TPU node in the pod has 4 cards, yeah, and then the TPU pod has 1,000 cards or 256 nodes. Now, the memory bandwidth is where things become very special. The memory bandwidth of one chip, one TPU chip, is 5 terabytes per second, and that is achieved by 16 HBM2 links. And you see each MXU has its own high bandwidth memory, yeah, and the high bandwidth memory achieves at least 300 megabytes per second, gigabytes per second, and so you get 5 terabytes per second per card, I should say. Per node it becomes 4 times more, so that brings you to 20 terabytes per node per second, or 5 petabytes per second for that pod with 256 nodes. And the flops similarly reach incredible numbers. So one TPU card has 100 teraflops per second. The node gets 400 and the pod gets 100 petaflops per second. So let's just stop here for a moment. 100 petaflops per second in 256 nodes. Yeah, 100 petaflops per second is roughly the #1 machine on the top 500. And yes, there are different floating point formats used and so on, so it's not an apple-to-apple comparison, but this is way ahead of HPC. Yeah, in 256 nodes, there is a lot of compute power and memory bandwidth here.
Peter, is that 64-bit double precision, or is that something else in this case?
No, this is, I'm not 100% sure that it has been specified. So it started with the option, I think, of 8 or 16-bit precision with a new Google format called the B float, for a brain float. Then they went to a 16-bit and 32-bit combination, I think, for the V2 chip. But the details I do not exactly know, but it's definitely not 64-bit floats. However, one of the interesting lessons that the HPC community is already learning from the machine learning effort is that often you don't really need these 64-bit floats. They are a luxury, yeah, but they're ultimately quite costly. And at another point in time, I will tell you what we're doing in the SKA processing to basically reduce the memory bandwidth by using these lower precision numbers carefully. Even the computations can be done at high precision. Yeah, inside the compute chips, there's plenty of speed, but moving the data in and out is extremely costly. Yep. And so by the way, the 5 petabytes is an honest 5 petabytes. So if you have smaller numbers, that goes even further than it already goes. Yeah, and 5 petabytes per second is a lot of memory bandwidth. So this should raise eyebrows, and we'll get back to a few more speculations about this in a minute. I just want to look at the left bottom of this graph and of this slide where we talk about operations per clock cycle, but that's because that's really the new thing. So a CPU has tens of operations per clock cycle through pipelining and cores. Yeah, so you usually have tens of cores now, and by pipelining the instruction, roughly one result comes up every clock cycle. If you vectorize your operations, you get maybe a vector depth of some, say, hundreds or so. So we get like on the order of 1,000 operations per clock cycle. GPUs enlarge that to tens of thousands, and TPUs to 100,000. Yeah, and so this is, I think, indicative of what is happening here. Yeah, the pipeline is even deeper than it was before due to the systolic array. On the right side, you see the instructions, and as I already mentioned, the instructions are really the TensorFlow operations. Not all TensorFlow operations, but quite a few can be invoked on the chip, and they are simply RPCs to the chip. Yeah, it's quite a new execution model but it works well here. And what you see here is, simple data movement commands, as well as maybe a matrix multiplication or some convolution or activation function that you compute for lots of elements of vectors or tensors. Yes, as we said, this is a big machine, and it should work quite well for moderate granularity computations like SKA and AI, for which it would make. It won't work very well for things like adaptive mesh refinement, because the communication overhead is probably much worse than it is on a traditional computer. But just like GPUs in 2003, this looks like a platform to me that is definitely worth tinkering and playing with to see its potential. It may not be quite there at the moment. For example, the precision of the numbers may not be right. And yes, it may ultimately require a new version of the TensorFlow chip to make these adjustments, but the promise is definitely there. And some of the candidate enablers that may still need to be created are, does HPC need more operations than the TensorFlow operations? Perhaps they don't, is my feeling. There is a lot in the TensorFlow operations that is directly mapping to HPC calculations. Is a more general systolic network needed? And it may be needed, I think, for particular kinds of graph computations, but there are lots of computations for which the available systolic interconnect in the matrix multiplication unit is actually good enough. Mixed precision arithmetic would really be the best, where precision can be adapted as parts of the computation flow by. I think this is looked at a lot in connection with posit numbers, and the RISC-V community is fairly hot about it. I hope that takes off, but it's early days to say if it really will be successful. For SKA, this could be a breakthrough. They've been looking at huge computers where not 5 petabytes of memory bandwidth is needed every second. So not 5 petabytes per second, but 200 petabytes per second. And so here you, for the first time, see 40 pods would do it. 10,000 TensorFlow nodes. It's the first time we see something that is within reach, at least. Previously we were looking at hundreds of thousands or millions of machines. So that's definitely worth exploring. Even though it's not likely perhaps to work immediately, there's a lot of promise here. I think we're coming to the end. TensorFlow is something to enjoy. Go read about its wonderful project structure. What was built? How does it all link together? It's so thought through. It's just it reads like a novel when you go through the documentation. It's very easy to play with it. Google's documentation is extremely good. I think that a couple of lessons here is there could be significant cost benefits here. And this is really custom hardware for a particular domain. It's not completely general purpose. Another lesson is this is a project that's not easy to do again. The amount of resources poured into it have been very large. Very, very clever people worked on it. And but there's a lot of promise here. Good. I think that's where we should stop.
Okay.
Thanks.
Well, Peter, a lot of questions come to mind with the potential of this. I remember when I saw your talk in South Africa, you mentioned that some of these techniques are not new, that they came from the 60s or 70s. Did I get that right?
Yeah, that's right. In those days, people already realized that making deep arrays of processing units that are connected with a network can eliminate a lot of writing to memory, to SRAM within the chips. And that's actually a very energy costly operation to do. And so, yes, these architectures have been lying around, and there are many, many variants of it. Some very beautiful mathematical ones that have like perfect parallelism, like many elements working in complete synchrony, never overloading network connections. And so, for example, networks have been discovered that have at most 2 hops or at most 4 hops. They are rarely ever used, I think, at the moment, but they're obviously very attractive for evening out the workloads. And these things are ancient. Yeah,
Yeah.
they're from the 1990s, 1980s, and it's lovely to look at it
Yeah.
actually.
Yeah.
Good thinking. Yeah.
Well, Peter, in terms of data flow and data management, which I didn't see as part of this really, I mean, you're going over a PCIe bus, right? Which doesn't have anything close to these kind of bandwidth numbers. How are they getting that done? Does the data come in and just crunch until it spits out some kind of output?
So let's see. So the cards are quite carefully architected to get 30 gigabytes per second into the card. So if you go to the extra slide, there's a TPU block diagram, which, by the way, I took from a Google presentation. So what you see that what we see on the left is 15 gigabytes per second for the V1 TPU, and I think that has been doubled for the V3 or the V2 already. So that is the bandwidth per card. So now, yes, you will want to do computations that do enough on the data that this is a reasonable pipe, into the PCI bus. But it's not so bad. 14 gigabytes per second per card is 60 gigabytes per second per node. That's not very different from the normal DRAM memory bandwidth of a computer. And then what you see internally is that the bandwidth on this first TPU into the matrix multiplier unit is 160 gigabytes per second. That was before they used HBM, and so this more than doubled, I think, with HBM from version 2.
Well, Peter, these devices right now are only available from Google through the cloud. They don't sell these chips, right? Is the future Google Cloud? Is this going to be? You think this will be the only way to get at these capabilities?
Well, I don't really know what to think about this. Of course, everybody knows. So to some degree, is it very difficult to be beholden to a chip that you can't ever rebuild, or to a chip that you can't touch because it's in the cloud? I don't really know to what degree you want to control this. Yeah. Another way of looking at it is that Google's design is out there. There's a wonderful paper by Dave Patterson on this chip, where he describes the team's effort. And so I would imagine that some of the other machine learning processing units that are currently under development would have very similar mechanisms. And we see that, for example, in the latest NVIDIA chip. Yeah. So yes, there is possibly a problem here. You could also say this is the future, and you don't really have to worry about it. The resource is available to you. People will take different attitudes about this, I think.
Yeah. Wow. Well, Peter, this is very exciting, especially in terms of things like the SKA telescope that have these unimaginable data requirements and computation and everything. So, and machine learning just eats data for lunch, as I like to say. Right?
Yes.
Yeah. Well, Peter, I'm really looking forward to hearing more about this as you learn more and work more with folks to see where this is going to go and play around with it. I guess, what are your next steps after this talk? What would you say?
So I'm encouraging some graduate students at a few universities to play with this and maybe do explore some true HPC algorithms and see how efficient are they on this platform. So I can't find anything yet. So it must have captivated many people, the idea, but the work still needs to be done. Those look like projects that are very reasonable to do. I think exploring a few libraries with benchmarks or so should be possible. And I think then we have to sort of see what is really blocking using this. Is this really a candidate, or do we have some missing things? And see if we can get some interest from the community at Google to make changes if needed. Yeah, but at the moment, I think we just don't even know yet.
Well, I love your parallel to looking at the GPU chips,
Exactly.
right? I
Yes.
mean, the idea that it could be used for computation was just a theory, and look at it now. The biggest supercomputers in the world are based on these devices. So,
But when you look at the early efforts, there weren't these, very clever hackers that used graphics operations to do calculations.
hmm
This didn't have a smooth start with CUDA being there.
yeah, yeah.
Yeah, this is, yeah, and I think we're in the very early days of looking at this as a possibility.
Yeah, yeah. Well, Peter, hey, I really want to thank you for doing this talk again for us here on Inside HPC, and we're looking forward to hearing more from you.
Okay, great. Thanks very much.
Okay. All right, folks, that's it for the Rich Report. Stay tuned for more news and information on high performance computing.